Welcome everybody to the class Stochastic Processes 1 at the University of Leipzig in the summer semester 2020. The class is meant for students in the mathematics diploma degree of year 4 and higher, and for the students who are in the program Master of Mathematical Physics that we run together with the colleagues from the physics department. Stochastic processes in mathematics is the theory of systems or quantities which evolve over time under the strong influence of randomness, which has the effect that we cannot make precise predictions on the outcome of these evolutions, but we can make at least statistical predictions or statistical measurements. And the theory that we shall present is about those statistical measurements and how we can compute things. And as you shall see, there is a really enormous amount of mathematical theory which comes from different subdisciplines of mathematics which comes into play, which makes the whole thing a really rich and rewarding theory. Not only from a purely mathematical point of view, but also from an application point of view. Well, examples of such stochastic processes can be found everywhere. For instance, it can be the price of a share on the stock market, which evolves over time. It can also be the molecule or an atom which evolves in a gas in space. It can also be an ensemble of molecules which see each other and which interact, but still with a certain amount of randomness involved. It can also be the theory or the mathematical model of a disease which spreads in a socially extended system. So you see that there's really enormous abundance of examples and also of practical need to understand stochastic processes. And we shall encounter and we shall develop theory, or a large amount of theory, which is very useful for the analysis of such phenomena. The course will be conducted in the way that I shall produce 2 videos per week of 90 minutes approximately each, so the usual academic double hour. And I shall put them online on YouTube, where you can download them at any time of your choosing, which fits best to your daily schedule. You can also watch them repeatedly, which will probably help whenever I'm not clear enough to understand after you have seen my desperate explanation a couple of times, which then probably will help you to understand what I probably really meant when I said all this. So you can watch it anytime at the speed you like. That's certainly an advantage. And another advantage is that once the videos are produced, we can reserve the energy and all the time that is left for real direct communication. And this can be done most preferably through this online platform Moodle, which is the central platform of the University of Leipzig for this online communication and online teaching. You can find links to the videos on this platform. Once you log in there and look out for the class Stochastic Processes, you can find there also the lecture notes, which are the basis for my lecture. And you can also find the exercise sheets, which you are supposed to look at every week and try to find your solutions to it. So on the Moodle platform, you find the scripts, the lecture notes, which is the lecture notes. You can find the assignment sheets, and you find the entry point to the forum, which is the place, the digital meeting place, where we can all meet and exchange our comments and also questions regarding all aspects of the lecture. It might be regarding the actual way we present things and the way we communicate, but it also should, of course, involve a discussion about the actual contents of the lecture. Right, so that is for the general organization of the lecture. I shall get started with the first lecture now, which from then on will be a presentation of the material on my tablet as handwritten notes, and then I shall explain to you while I'm writing it and while I'm editing my handwritten notes the contents of the lecture. So in that sense, it shall be kind of similar to a classical lecture in the classroom, except that you will not see me directly, you will only hear my voice and see as the things that I write down on the tablet. Right, so that's approximately how we're going to be doing it. I'm looking forward very much to communicating with you on this new type I think not all aspects of this new type of teaching are bad. In fact, I'm kind of curious how this will work out, and I'm kind of optimistic because this is a new fashion, a more democratic fashion, and a more honest way of communicating with each other. One-way communication is really condensed to these videos, and everything else will be two-way communication, which is also from the lecturer perspective, obviously much more rewarding. So I'm really looking forward to doing all this with you and learning with you and from you. And I hope we will all grow in the course of the next weeks, which we will spend together with this class. So now we get started, and see you next time. Stay tuned, and now we'll start with the actual first bit of material of the class. So welcome everybody to the first classroom session of our lecture Stochastic Processes 1 at the University of Leipzig in the summer term 2020. We want to study stochastic processes, and I want to start by giving you some examples or some domains where stochastic processes naturally appear, and why it is so interesting and so important to look at them. First example is stock price dynamics. So here I have depicted or downloaded for you a picture of a typical stock market dynamics, which is taken over the course of several months. In this case, is the Coca-Cola stock price on some stock exchange, and you see there is this curve with up and downwards motion, and it appears that at one day you cannot predict what the level of the stock price will be on the next day. You cannot make a precise prediction, but there seems to be some structural repetition here in the curve as we watch it. Also, we observe that there's a certain tendency in spite of all the randomness. So there's things to study here, and of course it's very important because the better you understand these curves, in case of the stock market, the better you will be in your business. The second example is very related, in fact, to the example number one, but it comes from physics. This is the example of diffusion of molecules. So here I've downloaded some more or less random picture of diffusion of molecules. Here would be some experiment where you have red and blue particles in a box, and there is a separation wall between the two types of particles. At the beginning you remove it, and then you see how the two families or the two species of particles mix up as time evolves. And they do it in a random fashion, but there's a lot of structure there in spite of all the individual randomness. But obviously this is a process where randomness is strongly involved. And the similarity or the between the example 1 and example 2 is essentially that on an individual particle level, if you just fix, for instance, one of the blue particles in the example 2, then each individual motion of one of those blue particles is, or a red if you like, is essentially the same as what we see above for the stock price, although that will be a motion in 2 dimensions. So you would get one realization of a blue particle motion if you considered an investor who owns not only one stock but who owns 2 stocks, and you write in X and Y coordinates the actual position of the 2 different stocks. That would give you a random motion in 2 spatial dimensions, and that is more or less exactly the model for an individual blue particle in the gas here, which we have seen in example number 2. Another huge branch of physics or mathematics, and hence in nature, where random processes appear, is the field of statistical mechanics, or non-equilibrium statistics, both equilibrium and non-equilibrium mechanics, in fact. So the most frequent subjects where these things appear are the theories of magnetization, crystallization, or percolation. And as for the picture which we see here, you could think of this as a snapshot of the evolution of a magnet, of a 2-dimensional magnet who has dipoles which can point upwards and downwards relative to the two-dimensional surface. And you could imagine that this magnet at initial time was prepared in such a fashion that on the left-hand side you had a perfect rectangular green domain, which would correspond to all magnets there pointing upwards. And as correspondingly at t equals 0 on the right-hand side, you would have all gray, a rectangular domain of all gray magnets which point all downwards. And then you heat up the magnet, and then the magnets start to interact with one another, in particular at the boundary, where you have the transition from green to gray, and then you have a fighting going on the boundary line between green and gray, and the green want to pull the green want to pull the gray towards the red color, and so forth. So you have this fight, if you like, going on, and what you will see is this random curve, which is evolving over time, and this random curve, or the whole shape there, is of course very important if you ask for the average magnetization of the total magnet, for instance. This is a typical picture you see in these theories, and quite obviously there's enormous amount of randomness involved, a huge number or a huge degree of randomness, because each of these individual guys, again, each of these individual magnets is performing some sort of a random motion, which is also influenced by the random motion of all other, or the random behavior of all other magnets in the vicinity, if you like. The next example where stochastic processes appear is the theory of growth processes in general. So that would be very general. So let me give you an example. If you look at this picture here, you would probably think that this is a snowflake, which you can observe sometimes on windows in wintertime. And of course, you have various shapes of snowflakes, and the snowflake, each individual snowflake, will grow under certain conditions of temperature and so forth, and humidity. And you ask, how will that grow in the next moment of time? There is again no precise prediction possible how that thing will grow and how it look like exactly in 20 minutes from now or something. But of course, there's an enormous amount of structure here, and you would like to make reasonable and valuable statistical statements about the most likely shape and so forth. And you would probably, in a refined analysis, not only want to make statistical statements, you would also want to make statements which will be true for all such snowflakes, but that might still involve a statistical analysis in order to come up to conclude in such a very fine fashion. Okay, so that would be the theory of the growth of snowflakes, if you like, but in fact it's not only about snowflakes. You could think of this being a schematic picture of a genealogical family tree, or a picture of a tree from genetic models about certain species and about genealogical proximity of species and inheritance. Or you could also think of this graph, in fact, as a graph of a social network, where a connection between two vertices of the graph is drawn when two individuals know each other, and that would be here then the growth of a certain social network. In fact, the social network would be slightly more general, typically, because it would not only allow for tree-like structures, but for more general structures where you have links between people across different leaves or different branches. But for the easiest of all cases, you can assume that you have a tree which grows over time, and then what you see as a realization of your growing social network would be such a picture. So that's, if you like, tree-valued or graph-valued stochastic processes. If you are not so interested in some geometric representation, but more in a combinatorial representation, you might sometimes also encounter pictures like this under 5, where you just recombine certain genealogical information in a graph and depict it. So in a way, the pictures that I have drawn here under 5 are very similar in spirit to picture number 4, and they appear in the theory of genealogies of species and certain phenotypes, if you like. These are also randomly growing trees, and if you want to ask for biological proximity of certain species and so forth, you would need to study such graphs, because you would want to study the question how likely it is that certain species have a common ancestor at some point in the history of evolution of species on the planet. Another application from mathematical biology would be all these huge literature and theory about the theory of the spread and growth of populations, or of viruses, or of information, which is obviously very important very much today, or in these times. So these are mathematical models which try to model, as I had just said, how a certain virus, say, would spread over a certain territory, where the virus is carried by individuals who travel in a random fashion, who meet with other individuals in a kind of random fashion, and who during such meetings can or cannot transmit the virus or not. They can be cured within a certain period of time, or they can get reinfected, they can die, they can give offspring to other individuals, and so forth. So that's a huge playing ground for both theory and application. And it is very important, and it is a very active research field, of which I'm personally not an expert, but we shall probably encounter here and there an example in the easiest case during the course of this lecture. The next example, which I chose, would belong to the field of fluid mechanics, or if you like, turbulence theory, where we believe, or some people believe, that in the turbulent regime, fluids are subject to real atomistic randomness, which then bridges all scales, such that what we see in the end on the macroscopic scale is really the effect of the microscopic atomistic, or if you like, quantum randomness. And the mathematical description of such turbulent models is sometimes done by so-called stochastic partial differential equations, which is the theory of partial differential equations under the additional influence of thermal noise, which then leads, as I just said, to so-called stochastic partial differential equations. So it will be dynamical systems in infinite dimensions with additional random forcing terms, for instance. That's how modern theories try to get a grip on this still very challenging and basically unresolved problem of a mathematical description of turbulent fluids. Of course, these kind of questions also appear on larger scales in meteorology, where weather in general is a huge stochastic process with a huge amount of degrees of freedom, and only simplified models can be treated, but obviously they can be treated in a very precise fashion nowadays, which give very interesting and very good predictions. It's impressive how good meteorologists have become in predicting the weather for the next days, or for even longer time scales. The final example, which is very beautiful, but for me as a mathematician still very mysterious, essentially related to everything that's coming from the physical side, is the field of quantum field theory. In quantum field theory, you try to describe and make predictions on, say, high energy physics experiments. This is done by in the constructive quantum field theory by constructing what the mathematician would call a probability measure on an infinite dimensional state space. The easiest example of this is the so-called Gaussian free field, which is a Gaussian measure on a Hilbert space. And here we have seen exciting new developments over the last 10 years, say, where the mathematical theory has made great steps towards a rigorous mathematical understanding of these physical constructions, which are semi-mathematical, let us put it this way, but still very useful for the field of physics, but from a mathematical point of view, very difficult to understand and probably not perfectly rigorous from an orthodox point of view. Anyway, in mathematics we have made huge progress with regards to making rigorous sense to some of these constructions that are being used in physics since long. So other buzzwords here are path integrals and Feynman diagrams that you use in order to do computations in quantum field theory. So that's a huge domain, and fortunately in Leipzig we have some superb experts in these fields who bring their expertise together. So Leipzig is a good place to study such questions. The mathematical theory which comes into play here in this connection is again the theory of stochastic partial differential equations. So I hope that this collection of examples was colorful enough for you to understand that there is a huge amount of different types of stochastic processes, and that you get interested enough in order to join me, and that you will undertake the effort to learn some of the terms and concepts and language elements, which would help you to have some sort of a unified picture on all these phenomena, which sounds quite challenging and almost impossible because the presented examples are so diverse, but you will see that there's a very useful fundamental language that was developed in mathematics over the last, say, 100 years, which is quite useful and quite rewarding to understand many of all these phenomena from a unified perspective. And that will be the aim of this class and of me as your advisor and your lecturer, to provide you with this unified approach. For this, of course, we have to learn and get used to the language of probability theory in general, and the contents of the first two lectures, or the remaining lectures of this first week, will basically to go through the most fundamental concepts of basic probability theory together with you as quickly as possible in order to start with the actual theory of random systems as they evolve over time. So let's jump right into the matter of this course and define what we understand by a stochastic process. Given a probability space, omega fp, a stochastic process is just a family of random variables defined on that probability space, assuming values in a fixed measurable space S, which is equipped with a Sigma-Algebra curly S. So let omega fp be a probability space and I be some index set. Let S, curly S, be a measurable space. Then a family of random variables, xi, where I ranges over the index set I, and each xi is a random variable from an omega to this space S, then this is called a stochastic process. This is a very general definition. A stochastic process is nothing but a family of random variables, And this will be the most general definition of a stochastic process that we will use. It is very general, and we will specify in the future certain subclasses of stochastic processes in order to be able to do some interesting theory. But in order to accommodate all different instances of stochastic processes, this very general definition is very useful. Now, I assume that not everybody is completely familiar with all the elements which appear in the definition above. And in order to familiarize ourselves with this very abstract definition, we would probably want to understand or recap what a probability space is. We would want to recap what a measurable space is, and we would want to recap what a random variable is. Once we have understood these three pieces, we will fully appreciate the definition of a stochastic process. So we see that we have to invest a little bit in order to understand this definition. The first step we have to make is to understand the concept of a probability space, which is of course the most fundamental concept in probability theory in general. So probability space is the object that we introduce in mathematics to describe a simple or not so simple experiment which involves random outcomes. So let me recall this definition to you of what a probability space is. A probability space consists of a triple omega fp, where omega is a set. The set omega is the collection of parameters for all the outcomes we can observe when we conduct an experiment with random outcomes. And therefore it's called the set of realizations. So whenever you observe an experiment which has a collection of outcomes, you need a container set in order to parameterize all possible outcomes. So for instance, when you toss a coin, you have two outcomes. So omega will be the parameter space in order to describe these two outcomes. And the more complex the stochastic or the random experiment is that you want to describe, the richer the set omega needs to be. F is the second ingredient of a probability space, and it is a subset of the power set of omega. So F is a set of subsets of omega, which will satisfy the additional requirement of being a so-called Sigma-Algebra. And this is what we call the set of events which are associated to this random experiment or to omega. Let me give you an example of such an event below. But let me say here that an event is just a collection, a typical event is a collection of possible outcomes of the random experiment. So if omega is the set of all outcomes, then an event is a subset of all outcomes. So an event collects a certain subset of all possible outcomes and defines this as an event on which I, for instance, could place a bet at some betting agency. And finally, P, that's the third ingredient of a probability space, is a function which assigns to every event a number between 0 and 1, which is interpreted as the probability for this event to occur. We will give examples below for this triple. But let me try to explain to you once more the meaning of these three elements. Omega is the set of all possible outcomes of a given experiment where the exact outcome is not predictable completely at the beginning of the experiment. So omega collects all possible outcomes. F is the collection of events, and a typical event is a collection of possible outcomes. If you place a bet on a random experiment, then effectively you place a bet on a collection of outcomes, which provides success of the bet. So each bet is essentially a bet on a collection of outcomes. And we identify the bet with the corresponding collection of outcomes. And this collection of outcomes is then a subset of all outcomes. So it is a candidate for an event as a subset of omega. And P, finally, is a function which measures the size of an event, which, in other words, measures the probability for the event to occur. These three elements are what we typically need in mathematics to describe a random experiment, or an experiment with a random outcome. Let me give an example. One of the simplest types of examples that you can think of. Let us think of the example that you sample from an unbiased random generator, a random number generator, which each time you hit it or you kick it will generate in an unbiased form a natural number between 1 and 7. And now the experiment which I want to define and want to describe consists of using this random number generator 3 times in order to provide a sequence of 3 consecutive numbers, A, B, C. So what is the set of all potential outcomes of this experiment? The set of all potential outcomes of this experiment is exactly the set of all triples A, B, C, where A, B, C are numbers between 1 and 7. Let me say it again. So my random experiment consists of using the random number generator 3 rounds, 3 times, in order to generate a sequence of 3 numbers. The beginning of the experiment is the first use of the random number generator, and the experiment ends after the 3rd use of the random number generator. And the result of the individual experiment is a concrete sequence, a precise sequence of 3 numbers A, B, C. Hence, the set of all possible outcomes is the set of all such sequences, all such triples. As a set of events, I take the full power set of all these possible triples. Let me give you an example of a possible event. Assume that you want to bet on the event that the chosen or the selected or generated 3 numbers in the 3 rounds A, B, C sum up to a number no less than 11. That's probably a reasonable bet you can place. So you have this random number generator, you want to play with it, and you want to offer a bet to some of your friends, say, and the bet says, okay, if I hit or if I use this random number generator now 3 times, and if the sum of the 3 generated numbers is 11 or more, then you should pay me a euro. That would be some sort of a bet. It is reasonably formulated, and this bet actually is a bet on a collection of outcomes which yield success, which yield the euro. So in that regard, this bet E is equivalent to the collection of all possible outcomes among is a collection of certain outcomes among all possible outcomes, which will produce success of the bet, which will produce the euro being paid to you. In that regard, the event is equivalent to this simple 0 or 1 event, which is correction. The bet is equivalent to this 0-1 payoff, and the 0-1 payoff is equivalent to the collection of all possible outcomes which generate the payoff 1. Therefore, the bet is equivalent to exactly this subset of all the bet is equivalent to this subset of all possible outcomes. So the bet is equivalent to a subset of omega. In fact, in the current situation, in the current example, I could try to offer a bet on every possible subset of outcomes. Hence, my collection of events in this case will be the set of all possible subsets of omega, which is what we call the power set. And finally, the P function, which assigns a probability value to an individual event, here in our case would be just the size of the event measured in terms of cardinality of this event relative to the cardinality of all possible outcomes. This definition produces a function on the set of all events, which is what we would call the probability. So, if we have a bet on an event which is relatively big, which in other words means that there's many triples which would produce success, then the probability of that event should be bigger than a probability of an event which has less elements. So here in our case, we just say that the probability of a certain event is defined to be the size of the event in terms of its cardinality. But for the number or the probability to be a number between 0 and 1, we normalize. So therefore we compute the relative size of the event E relative to the total size of the set omega, so relative to the cardinality of omega, which is the number of all outcomes. So this rule, which we have described here, is the old rule that you know from school, that the probability of success of a certain event is just the number of positive or successful outcomes relative to the number of all possible outcomes. Now, in the definition of a probability space, we had two additional details which we have overlooked at this moment. Namely, the one detail is that the set of events which we want to deal with is what we call a Sigma-Algebra. Let me recall to you what that actually means. A subset of the power set of a given set omega is called a sigma field if the following three conditions are satisfied. The empty set is an element of the Sigma-Algebra, of the set of F. Second, the set of events F is stable under the operation of taking complements, which means the following: so that if you can place a bet on a set of results of your random experiment, then it should be admissible also to bet on the opposite, which means that anything but an outcome coming from the set of outcomes E is what you bet upon. And the third property which we want to make sure for the set of events that we want to deal with is that the set of events is stable undertaking the union, the countable union of sequences of events. So in other words, if we have a sequence of bets or a sequence of events, then we can talk about the set theoretic union of these events. And what we want is that the set theoretic, or just the union of these events, is again a proper event. So if you want to formulate or rephrase these three conditions in a real-life situation, for instance, you could think of these events or this sigma field of events describing the set of bets, of simple bets, of 0-1 bets, that a certain betting agency would accept. And what we want from our betting agency, where we want to place the bet, are the following three conditions, or the following three properties. We want that the betting agency accepts a bet on the empty set, which means that we bet on the empty set of outcomes. In other words, if we have a random experiment which has a collection of possible outcomes, then the betting agency would accept that we bet on an outcome which isn't there, or which on the empty outcomes. So in other words, we would bet upon something which cannot occur. Whether or not this is a sensible bet, we want that the betting agency will still accept the bet. We are not asking about any price or so here. We're just asking whether, when we go to the counter of the betting agency, the agency would accept our request that we want to bet that the outcome of this experiment, that there will be just no outcome on this experiment. The second thing that we want to require from our betting agency is that if the agency accepts a bet on a certain collection of outcomes, then it shall be also admitted to collect on the opposite, which means of the set theoretical opposite, which means that we bet, we take the counterposition of the bet, so to say. And the third condition we ask is that if the betting agency accepts a sequence of bets, then the union of those bets should also be an admissible bet. So what's the union of a bet? The union of a bet is successful if at least one of those bets is successful. So we have a sequence of possible outputs or possible outcomes, and what we want is that the union of all those outcomes is also a possible bet that we can play. These three conditions are the conditions we require for a sigma field. And we want to make sure that these conditions are met in the future. And finally, there is the condition, or there is in our description of a probability space, there is this notion of a probability measure. So when are we calling a set function, a function which is defined with certain sets? When do we call that a probability measure? We call it a probability measure if the probability of the full set of all possible outcomes is 1. Well, why is omega the full set at all a set on which we can apply the p function? Well, we want that the p function is defined on all elements of f. F contains the empty set, and by condition 2, F also contains the complement of the empty set. The complement of the empty set is omega. So therefore we can apply the p function to the full set at all. And what we require is that the value of the p function of the full set is exactly 1, which in terms of our probabilistic interpretation means that if we place a bet on the event that we observe something at all, then this bet should have a success probability of 1. The bet on omega as an event is also sometimes called the safe bet, and omega is called the safe event. And the second condition that we want from our p function, in order to call it a probability measure, is that it is countably additive, which means the following. If we have a sequence of events which are mutually disjoint, and if we consider the event which consists of the union of all those events, which by condition 3 on a sigma-algebra is a proper event, which means is an element of the
sigma-algebra F, then we want that the P function evaluated on this new event is nothing but the sum of the P values of the probabilities of the constituent events EI. So if you want to draw a picture, it would probably look like this. So if omega if that's your full probability space, and you have a sequence of events starting from E1, E2, E3, and so forth, which is done in such a fashion, or which are designed in such a fashion that they are mutually exclusive or mutually disjoint, then you get a sequence of bubbles, and since these bubbles are mutually disjoint in the way you would imagine that these bubbles get smaller and smaller, and you can pass to the set which consists of the union of all these bubbles. So the union of all these bubbles, by property number 3 of our sigma-algebra, is still an admissible event, and we can ask for the volume or the probability of all these bubbles, where the bubbles are called EI. And what we want is that the volume or the probability of these bubbles is nothing. Correction, we want that the volume of this union of bubbles is nothing but the sum of the individual bubble volumes. This sounds like a very natural condition, and it sounds like something like a redundant condition, but there are examples, and I shall present on a superficial level at least an example below, when you will see that sometimes you may encounter situations when such a naive request and such a naive requirement is actually not satisfied. And irrespective whether it is superfluous or not to require condition 2, this countable additivity, we want to make sure that this countable additivity for a probability measure is satisfied. Okay, so the P function that we are the P functions that we are dealing with in probability theory, which will be interpreted as assigning a probability to an event, they are required to satisfy this countable additivity condition. And once they are, we call them probability measures. So finally, we have recaptured completely what we understand by a probability space in mathematics. Let me recall this or repeat it. A triple omega Fp is called a probability space if omega is a set and it models, or it stands for, the collection of all possible outcomes of an experiment which is conducted, or which has random outcomes. So there, for each run of the experiment, we have a whole range of possible outcomes, and omega is exactly a parameterization for all possible outcomes that we may observe. F is the set of events which are triggered by these possible outcomes. In other words, F is a certain subset of the set of all subsets of omega. And P is a function which assigns to each event a number between 0 and 1, which is understood as the probabilities for this event to occur. Many experiments in nature have more than finitely many possible outcomes. In fact, many experiments in nature have even uncountably many possible outcomes. And whenever we are facing such a situation, we need to be a little cautious when we want to construct a probability space for the description of such experiments. We have seen in the previous example, in the simple example of a finite probability space, that somehow the concept of the probability of an event relates to the idea of size. And now if we want to deal with random experiments which can assume values in Euclidean space, for instance, in continuum of possible outcomes, then a natural concept of size is the concept of volume. However, volume is a more complicated concept than it seems at the first sight. And this is exemplified by the so-called Banach-Tarski paradoxon. The Banach-Tarski paradoxon is a construction where a unit ball in dimension 3 or higher is decomposed into finitely many pieces, which then can be rotated and shifted in Euclidean space in order to give two identical copies of the initial ball from where they were taken. This would certainly yield a contradiction to a naive idea of volume, because through this decomposition and reassembling procedure, we would be able to all of a sudden double the volume of a ball, because we would be able to decompose the initial ball into pieces and reassemble those pieces in order to obtain two balls. Hence, since we shift around only pieces, which is a process which preserves volume, we would have gotten a mechanism that doubles the volume of a ball. That somehow cannot be. This is the contents of the Banach-Tarski paradox. The paradox is resolved by the understanding that the fractures or the constituting parts of the decomposition, so the little fragments here, they are so complicated, although finally many, they are so complicated that there is no proper concept of volume. In other words, these pieces here must be so complicated that our naive concept of volume does not apply. And that is actually exactly the solution for the resolution of the Banach-Tarski paradoxon. It shows that we need to be careful when we want to apply our naive concept of volume to arbitrary sets. And for that reason, we need to introduce a proper collection of sets on Euclidean space, say, for instance, on which the concept of volume is feasible and will not lead to contradictions. And the set of sets for this concept of volume produces a consistent and workable theory will be the so-called Borel-Sigma field. The Borel-Sigma field is a collection of sets on Euclidean space which at the end turns out to be a Sigma-Algebra. And one way to define the Borel-Sigma field is to say it's the smallest Sigma-Algebra that contains the open sets on Euclidean space. Recall that a set on Euclidean space is called open if, whenever you have a point in the set, then there is a sufficiently small ball which still lies entirely in the set. That's when we call a set open. And the Borel-Sigma field on Euclidean space is defined to be the smallest Sigma-Algebra, the smallest Sigma field of subsets of Euclidean space, to which all open sets still belong. And one way to construct this smallest Sigma-Algebra, which contains the open sets, is by taking the intersection of all Sigma-Algebra, so the intersection of all systems of sets which are on their own a sigma algebra and which contain the collection of all open sets. Using the fact that the intersection of sigma algebras is still a sigma algebra, it is easy to see that this intersection of a family of sigma algebras is again a sigma algebra, and it is then through the condition that all these sigma algebras which are intersected are supposed to contain the open sets, then it's easy to see that this construction here, or this object here on the right hand side, is in fact the smallest sigma algebra that contains the collection of all open sets. So whether or not you like this construction, we can think of this set of Borel sets on the Euclidean space as some way of a generalization of the concept of an open set. And it's the minimal generalization of an open set to which, as it turns out, the naive concept of a volume is still applicable, such that we will find no inconsistencies when working with this concept of the volume. So the definition of the theorem which I want to present now is the following. So on RD, on the Euclidean space, let the set O denote the collection of all open sets. Then this intersection of all sigma algebras which contain the set of open sets is a sigma algebra, and it's the smallest sigma field containing the collection of open sets. And this is what we shall call the Borel-Sigma algebra on Euclidean space. And then the second part of the definition of the theorem is the following, that there is a unique sigma additive function, where sigma additivity is understood as in the previous definition of a probability measure. So there is a unique sigma additive function on the Borel subsets of Euclidean space, which maps each Borel set into a real number, and this real number is to be interpreted as the volume of this Borel set, such that whenever the Borel set happens to be of simple type, namely, for instance, happens to be just a rectangle, so just a Cartesian product of intervals in the respective dimensions, then this function lambda on such simple rectangles is just our naive volume function. In other words, on a rectangle, the lambda function is just the natural volume or area. And this set function lambda, which assigns to every Borel set a volume, then is called the d-dimensional Lebesgue measure. So again, let me say it again. On Euclidean space, we can think of the smallest sigma algebra that contains all open sets. This smallest sigma algebra is uniquely determined, and it is constructed, for instance, by taking the intersection of all sigma algebras that contain the open sets. Then there is a unique measure, so a unique sigma additive function, which generalizes the concept of volume to this generalized open sets as follows. This lambda function is a sigma additive function on the Borel sets. This means that countable union of mutually disjoint Borel sets is still a Borel set, and the volume behaves in this additive fashion as it should be if it is in alignment with our naive picture. And this volume function generalizes the naive concept of volume in the sense that whenever the Borel set on which we want to evaluate the volume function lambda is a rectangle, then this lambda function gives back exactly our naive volume value that we know from school. In other words, if we restrict the concept of volume to the sigma field of Borel subsets, then there is a proper and consistent notion of volume for these Borel sets. And as a matter of fact, this is the unique way to extend the concept of volume to more complicated sets than just, say, rectangles on Euclidean space. The need for such a restriction of the concept of volume to not every possible subset of Euclidean space, but to a certain subset of spaces, a subset of sets from Euclidean space, is exemplified again by the Banach-Tarski paradoxon. Let us now see how we can use the Lebesgue measure together with the Borel-Sigma field on Euclidean space in order to describe the random experiment, for instance, which consists of choosing a point at random in an unbiased fashion from the unit cube in three-dimensional space. So what we want to do is we take the unit cube and we want to sample a random point from inside the unit cube in an unbiased fashion. We describe this in the following fashion. Omega is the set of results, which is the set of all points in the unit cube, so the unit cube. The sigma field of events which we choose will be the sigma field of which is given by the Borel-Sigma field. We do this because this is the set of sets of which we have a reasonable concept of volume using the Lebesgue measure. That is our set of events. In the future, I shall denote by the Borel-Sigma field of a given space omega as above the smallest sigma-algebra that is defined on that space omega and which contains the open sets. This, whenever I want to talk about this, requires that I do have a concept of open sets on the set omega, which here, in the current case of the unit cube, is available. So here I choose f as the Borel-Sigma field on the unit cube, and finally as p function or probability, I choose the Lebesgue measure on the unit cube. This is a consistent probability space in the sense that I have defined a set of sets on which I have a reasonable concept of a volume, which in my case shall serve as the definition of probability. So this whole construction says that the probability that the chosen point, if it is sampled at random uniformly, the probability of the chosen point to lie inside a certain subset of the unit cube is exactly given by the volume of this subset. Another example which involves the Lebesgue integral, and we will see in the course of this lecture many more examples of probability measures which in one way or another involve the Lebesgue integral, is the case of a random sample from the real line according to the normal distribution. So what you want to do is you want to sample a point on the Euclidean line, but this time you don't want to sample it at random, in a uniform fashion. You want to sample it in a biased fashion. And the bias is constructed through integration against Lebesgue measure, but not integration against plain or flat Lebesgue measure, but integration against a Lebesgue measure perturbed by a weight function. And the weight function in this case, in the standard normal case, or the normal case, will be the Gaussian bell-shaped curve. So for the Gaussian bell-shaped function, we have two parameters which determine the precise shape of the bell-shaped function. The two parameters are m and and a real number m and the non-negative number v. And using these parameters, I can define a real valued function, which is defined as x goes to 1 over the square root of 2 pi times v e to the minus x minus m squared over 2v. This is a function which is, as I said before, this famous bell-shaped function, and sometimes we shall denote this also by gamma m dot v of x. So that's the Gaussian function for the given parameters m and v, and this will be our weight function for the definition of the Gaussian measure. As follows, we choose as a probability space the full real line, which is the set of all possible outcomes of this selection of a random point on the real axis. Here we also choose the Borel-Sigma field. And as a probability measure or p function, we define as follows: given a subset, a measurable, here a Borel subset E of the real line, the p value of that set is defined as the area of the shape that I obtain as the subgraph of this Gaussian function over the set E, which I want to measure. So in other words, if in the graph here, in the picture below, E is the subset of the real line of which I want to compute this given p function, I take the integral of the Gaussian function, which I had just introduced, integrated over E, which is the shape, which is the area of this green shaded domain. Hence, this distribution describes the probability, for instance, that this randomly chosen point of the real line lies in the set E. So if I now sample a point from this distribution, it says that the probability that the randomly chosen point lies inside this given interval, say E, this probability is given by the area of the green domain. But we have also other types of distributions or other types of probability spaces which are, for instance, discrete or countable, and not finite and not uniform. So one example of such probability spaces is the Poisson distribution. It's a very simple distribution and nice to work with. It's the distribution for so-called rare events, and it's, for instance, in physics it appears for the statistical description of radioactive decay experiments. So what you observe is the decay of a certain substance over time. And what you want to observe, or the actual observed quantity for this experiment, is the number of decay events in a given period of time. So you have a certain amount of substance and you put it in the lab and you ask yourselves, how many decay events will I observe in the next 5 seconds or so? So the observed quantity is a natural number. And for a given parameter lambda, the statistical description using the Poisson distribution is as follows. The probability space omega is the set of all possible observations, which in this case is the natural numbers including 0. This is a countable probability space or a countable set. And in the case of countable sets, a very typical choice for a sigma field is just a full power set. Unless you have very specific reasons, this would always be your natural choice on the countable set, omega. And now we define the probability measure on this countable set, and here in such a situation it is most convenient to give the precise, to define the p function on simple events which consists of only one element. So here a simple event of only one element means that you ask for the probability that you observe exactly k as outcome of the measurement, so that you observe, say, exactly k dk events in the next 5 seconds or so. And then the definition is that this number is defined as lambda to the k divided by k factorial times a normalizing factor, which is e to the minus lambda. That would be the definition of the probability to observe exactly k, the number k, as outcome of the measurement. And for a more complicated event, the definition then is necessarily by Sigma-Algebra that the probability for a more complicated event is just the sum of the simple events which constitute as a disjoint union the more complicated event. So the sum of the probabilities for the simple events, here the probability of an event E is just the sum of the probabilities of observation, those k numbers which are in the set E. This is the Poisson distribution. It's a distribution on an infinite countable set. The next example is not so exciting at this moment. It's just meant to show you that you can also do geometric considerations of it. Not all of this needs to be on some integers or on pieces of the d-dimensional space, or flat piece of d-dimensional space. You can also construct probability measures on quite general geometries. For instance, you could think of sending a rocket to the moon, say, as your random experiment, and the navigation system of the rocket is really poor, which means that in the end the rocket will touch down on a completely arbitrary point of the moon, and you want to describe the statistics of these corresponding observations. So your space of all possible observations is the collection of all possible touchdown positions. You ask for the position of the touchdown of the rocket. That's your observed quantity. Then you would choose as a model the two-dimensional sphere as a model for the surface of the moon. The sigma field you choose here would again be the Borel-Sigma field. This is a case where on the surface of the moon we have a clear concept of an open set, so we can talk about the sigma field which is generated by this open sets. And as a probability measure, we take the relative surface measure, or the normalized surface measure, as we say. So in other words, the probability that you hit a particular set E with the rocket is given by the size of the set E, and the size of the set here is just the surface measure of the set E normalized, so divided by the full surface measure of the entire moon, or the entire sphere, in order to get a probability measure which assigns probability 1 to the entire space. The next example is already straight to the matter of the cause. It's in fact a stochastic process that I want to construct now. The stochastic process here consists of generating a random sequence of numbers where the numbers can assume values between 1 and m. And I want to generate this sequence of numbers, this infinite sequence of numbers, by hitting again and again a random number generator that generates each round one of those numbers between 1 and m. And the consecutive runs of the random number generator have absolutely no relation, so I assume that each time the random number generator is started anew and has absolutely no memory. So what is an observation which I can do if I conduct this experiment? One observation is an infinite sequence of an infinite sequence of numbers. So my entire space of all possible observations is the collection of all sequences, of all infinite sequences, where in each position of the sequence at any time there is any possible number between 1 and m. This is a discrete set, but it is uncountable. And in uncountable sets, omega, I always need to apply some care when I want to define the sigma field, because the space is so big that it can potentially generate inconsistencies with regards to the sigma additivity, for instance. So the sigma field which I will use is the sigma field which is generated by the so-called cylinder sets. And if I talk about the sigma field which is generated by a certain set of sets, I do a similar thing as in the case of the Borel-Sigma field. I'm saying it is the smallest sigma field which is so big still that it contains the given generating subset. So here I want to consider as a set of events the Sigma-Algebra, or the sigma field, which is generated by the so-called cylinder sets. And a cylinder set is a set of sequences which is determined or defined only by looking at finitely many coordinates of the sequences. So that's a typical example of a cylinder set, which is given here. So a cylinder set is a finite, is just a subset of a Cartesian product of all possible sequences, but only up to coordinate number k. And after these k coordinates, the cylinder set does not put any restriction on the sequences for all further indices. So a cylinder set is a set of sequences which is determined by a set of conditions which apply only to finitely many coordinates of the sequences. So every cylinder set can be written as a subset of the corresponding k-fold Cartesian product of the alphabet, or of the set A to the m, times the infinite product of the alphabet for all further coordinates. This set, this collection of cylinder sets is not a sigma-algebra, but one can think of, and one can talk about, the smallest sigma-algebra on the set of sequences which still contains cylinder sets, and this will be the sigma-algebra F with which I want to work. And by some fundamental extension theorems, it will be sufficient for the definition of a p function on the full sigma field F. It will be sufficient to specify this p function only on such cylinder sets, which then extends in a unique fashion to a general set from the sigma field F, which is generated by this set of cylinder sets. And my definition for the probability of a sequence to lie in such a cylinder set is the probability that the randomly chosen sequence meets the requirements which are specified on the first k coordinates. So that, in other words, this sequence fulfills the conditions which are imposed on the first k coordinates, these conditions are described through a certain subset A of the corresponding Cartesian product, and therefore a natural definition for the cylinder set, for the probability for this cylinder set, is just to have the probability of those conditions to be met, and that's exactly the uniform distribution on the k-fold Cartesian product, where here the cardinality of the subset A is exactly the cardinality of those truncated sequences which satisfy the condition. It is then an exercise to check that this is a consistent definition, and then by what is called in mathematics the Carateo-Dori theorem, I can convince myself that this defines in a unique fashion a probability on the entire sequence set if I apply this p measure only to at least two measures of correction to sets which lie inside this particular sigma-algebra F. This concludes our first list of examples of probability spaces. We have seen that there may be very different types of probability space, but all of them fit into our general framework. So we have had a finite probability space with the uniform distribution. We had an uncountable probability set, probability space with uncountable with a uniform distribution. We had countably discrete probability spaces, and we had uncountably discrete probability spaces. All this are instances for the general concept of a probability space that we want to work with. The next concept we need to recall is the concept of a random variable. A random variable can be understood as a more complicated than just a binary bet on the outcome of a random experiment. And as, for instance, in the case of snowflakes, we can think of bets giving results not in terms of euro, so not in terms of Euclidean outputs, but also in terms of more general outputs, which assume values in general spaces or in general sets. And the concept of a random variable is the definition or the mathematical description of such a more complex bet. It's defined as follows: if you have a probability space omega fp, and if you have another target space S, which is equipped with a certain sigma-algebra sigma, such that the tuple of S and sigma is what we call a measurable space, namely just a set equipped with a certain sigma-algebra, then we call a map which maps the outcomes omega into elements of S a random variable, provided it is measurable. Where measurability means that pre-images of measurable sets in the target space are measurable in the domain space. So in formulas it says for all measurable sets on the target space, the corresponding pre-image under X is an element of our set of events F. So in pictures it's this: so if you choose an arbitrary set S from the sigma-algebra, which was defined on the target space, then you want that the corresponding pre-image, so the correct selection of all little omegas which are mapped exactly into this target set S, that this pre-image set as a subset of omega is a proper event, which is to say it is an element of our sigma-algebra F. A simple example is the example of this bet that we had before. So we choose at random a triple of numbers between 1 and 7. We write it as a triple of numbers ABC, and the output function we want to define takes the triple which was generated and computes just the sum of the entries. This can be understood as a random variable which maps the outcome of our experiment into another space. Here the target space is the natural numbers, which we equip typically with the power set as sigma field sigma here in this case. So that's such a band which has more than just a binary output. And since we equip both target and domain space with the full power set as Sigma-Algebra, the required measurability condition is automatically satisfied. An important case for such measurable maps or random variables is the case when the target space is just a real line. Then we can think of bets which compute actual output in terms, say, of money or other types of entities. And in this case, we talk about a real valued or real random variable. Now, the measurability of a random variable can be used to define what is called the law or the distribution, which is a probability space on the target space. That's in fact a very important concept because it describes the statistics of the outcomes when I observe the random experiment only indirectly through its effect on the random variable. So let x be an s-valued random variable, as in the situation before, where s is equipped with a sigma field sigma. Then we have an induced probability measure on the target space, which is called the law of x, or sometimes called the distribution, and which is defined as follows. The p measure of a set, the new measure, which is called px measure, if you like, the px measure of a set on the target space is defined as the probability that the random variable x assumes a value in that set S. Or in other words, the px measure of a measurable set on the target space is defined as the p measure of the pre-image of the set S under the map X. And this object, this px, as a new measure to measure sizes on the target space, which is induced under the map X, is called the law of X on S. So in pictures, it's what we had before already. Namely, if I want to measure now, and I can do that, I can measure now the size of a set S, provided it is measurable on the target space, as follows. I take the set S and I ask myself, what's the probability that under the map X, the chosen omega will lie inside the given set S, and I measure the probability. So in order to measure the size of S, I consider the corresponding pre-image, and I compute the probability of the corresponding pre-image set. And this will be my concept of a size for the actual set S. So effectively, I have introduced a measure on the target space S. And this new measure, which is also sometimes called the push-forward measure of P under the map X, is called the law of X. And if you think about it, you understand that this exactly describes the statistics of the realizations of X outputs. So you measure, in fact, with this law, the probability for certain outputs to be observed using the output function x. So the law of x is nothing but the statistical description of the collection of outputs that the map x can generate. So once more, Px of S is to be understood as the probability that the random variable x assumes values in the subset S of the target space. Let's give a simple example, slightly simplified as the example above, which was already very simple. So omega will be the set of triples with numbers between 1 and 3. So I want to consider now the experiment of a uniformly chosen random triple of numbers between 1 to 3. The Sigma-Algebra I choose is the power set, and the distribution, the probability measure I want to choose is the uniform probability measure on this finite set. I have in total 27 possible triples, and so the probability for a certain subset of triples shall be just the relative size, so just the quantity, the cardinality of that set in relation to the cardinality of the full set of possibilities. So that's my uniform distribution on this finite set as usual. And the random variable I want to define, I want to consider, is this summing up, the summation of the entries of these triples. As before, it's a random variable which maps the set of all triples, all admissible triples for this experiment, into the natural numbers, which will be my target space. And now this map X generates only 7 different outputs, namely the outputs, the minimal output of the map X is the number 3 when the chosen or when the generated triple is the triple 1, 1, 1. The maximal output of this random variable here is the number 9, which occurs when the generated triple was the triple 3, 3, 3. No other output than a natural number between 3 and 9 is possible. And we can compute now the probabilities of such outputs. Since there is only one possible triple that generates the output 3, its probability, or the probability to observe this output, is 1 over 27. Similarly for 9, or analogically for the output 9, but so for instance for the output 6, we have 7 triples, 7 possible among all triples, which generate in the end the output 6. So therefore the probability of observation 6 is 7 over 27. That can be done for all other possible output values, and you get this table here. This table can be used to define a probability distribution on the natural numbers. That's a discrete set which we equip with the power set, or a countable set which we equip with the power set as a sigma field, and it is sufficient to specify the distribution by specifying the distribution on simple events, on simple sets which are single valued, also have a single element, and we just say that for all k numbers in the natural numbers, px of k equals to the table here, to the numbers in the second line of this table here, and for all other values of k, we set px of k to be 0. This is then the full description of the distribution of this random variable, which we have introduced above. Another example where we have a continuum of values would be, for instance, our probability space to start with, which is describing a uniformly chosen point in the unit interval. And the random variable we want to consider, for instance, say, is to take the chosen realization, the chosen number between 0 and 1, and map it into its exponential. That would be a random variable which maps the unit interval, which is our omega, into the non-negative reals, and the probability distribution which is induced from this as law can be computed as follows. So we ask ourselves, what's the probability that we observe a realization of output which is in the interval AB? That's the same through the pre-image construction. That's the same as the Lebesgue measure of all omegas, which are mapped under the exponential function to the interval AB. And if I just invert the exponential function, this is the same as saying this is the set of all omegas omega who lie inside ln A to ln B. And since this is an interval, and the probability for omega to lie in an interval is just given by the length of the interval, this number is nothing but the difference of the logs, or the length of these intervals is just the difference of the logs, provided the numbers A and B lie in the admissible set of values which the function E can assume here. So it's easy to compute that. Another example, which is slightly more beautiful or so, is when we choose a probability space which describes choosing a point at random in a uniform fashion in the unit ball. So our probability space here would be just the unit ball in 2 dimensions. This is where we want to sample from. So it's the set of all points x, y in the 2-dimensional plane at distance no more than 1 from the origin. We choose the Borel-Sigma field as, again, as our set of events, and we take the normalized Lebesgue measure, so just the 2-dimensional volume measure, in order to define probabilities. In other words, the probability for a randomly chosen point to lie inside a set E is just the size of the set C as measured in surface divided by pi, which is the total surface of the total disk. And the random variable we want to define, or we want to look at, is just the evaluation of the x-coordinate of the given point. And then we can ask again for the distribution, which will be then a probability measure on the real line. And we ask what's the probability for the x-coordinate to lie inside a certain interval, say AB. Then geometrically this corresponds to, if A and B are chosen, corresponds to the computation of the surface of the area of a shape like this. For the random variable x to lie in the interval AB, this corresponds to choosing a point among all points of the unit disk whose x-coordinate lies in this slab, which is given by A and B, and this can be, for instance, computed by this integral here. The integral needs to be multiplied by 2 because we have the surface above and below the x-axis, and we divide by pi because we wanted to have a normalized measure which gives full mass 1 to the entire set. Often when we deal with random variables, we are in fact not so much interested on the actual random mechanism that generates the outputs that we see under the map x, when x is the name of our random variable. In many cases we actually do not care at all. We just care about the statistics of the outputs that we see through the random variable x. So therefore we completely neglect the specifics of the probability space omega fp and work exclusively with the induced distribution, so with the induced statistical description of the collection of outputs that we see under the map X. And therefore we even sometimes identify random variables provided they have the same distribution. For that reason, the following concept is useful. Namely, if we have a measurable space, so a tuple S and sigma of a space S with a sigma field sigma, and if eta is a probability measure on this measurable space, and then we call any random variable from whatever probability space it may come eta distributed if its law happens to coincide with a given eta. So we call a random variable of whatever origin eta distributed if its law is exactly the given eta. That's a simple concept, but as I said before, in many cases we shall not really ask for the precise generation or the precise construction of the random variable x. We just ask for its law, for its distribution. Now finally, after we did all this work in order to recapitulate some basic concepts of probability theory, we can come back to our first definition that we had in this lecture of a stochastic process and can fully appreciate it. And by this definition, a stochastic process is nothing but a family of random variables on a given probability space, assuming values in a joint target space S, which is equipped with a certain sigma field sigma. So let omega fp be a probability space and I be some index set, which could be, for instance, the non-negative time axis, and let S be a certain target space equipped with a sigma field curly S. Then a stochastic process for this index set is nothing but a family or a collection of random variables which map the outcome of this random mechanism, which is described by omega, into outputs which assume values in S.